Okay.
Greetings, everyone. The following is a conversation with Dr. Marcelo Maciel Amaral, research scientist in the domain of quantum gravity, on matters such as quantum gravity, quantum information science, topological quantum computing, and much more. Dr. Amaral, what is quantum gravity and why is it such a challenging area of study?
Okay. Thank you. Uh, so quantum gravity is a big subject in modern physics. Uh, Most research think this problem is an open problem for almost 100 years. So, which is we have general relativity and we have quantum mechanics. And can we put these two theories together? Or but there are different ways to think about this problem. I would say that probably the simplest one to communicate this is to say if can we quantize the gravitational field, where mathematically can we quantize the mathematical theory like general relativity is in one of its different forms. You can write that with different kind of fields, but can you use the quantization framework that works for quantizing other fields? Can you apply that to the gravitational field? And more general, people think about the unification program. Can you, by now we have successfully merged electromagnetism, the weak force, and the strong force. They are quantum field theories that you can understand them in the same framework. You have a classical field theory and you can quantize those fields and in the same framework. Can we add the general relativity? Can we add the gravitational field in that framework? So it's a kind of unification. So we think of this when you go to higher energy. So in our everyday classic world, we see the different fields doing different things, but they understand from like particle accelerators is at higher energy they converge to a unified field. And one of the expectations is if you go very high energy, if you go to the Planck scale, then also the gravitational field should uh, be merged to this unified field. But to get that, you would first need to deal with the first problem that I mentioned, the quantization of the gravitational field, because the other one are quantum fields. And there are different approaches to how you quantize the gravitational field, different solutions, but there is no agreement on a specific solution yet. There is not a specific solution that can be tested with current technology and can or even can be refuted. So there we will have different models competing for a long time until someone come with a clear way to test this this model, because like I said the the unification, even the quantum effects on gravity is expected to happen a very extreme situations. But another discussion is it possible in principle, or gravity is something pure classical, something pure emergent? And we have some frameworks, even though not direct connected with the physical world we know, but they are self-consistent, and mathematically they show that it's possible. So there are half-century works on different models with a lot of details that show it's possible. So I think the trend is to think it's possible, and we are looking to develop more details and to think how we can prove, how we can test this model. If you want, I can talk a little about the main ones.
Definitely. I'd want you to take a deep dive into explaining some of these models and frameworks.
Okay, the two main models that show it's possible to quantize the gravitational fields are currently string theory and loop quantum gravity. And they have done this job of this quantization come from different perspectives. Loop quantum gravity starts from the general relativity community way of thinking that space-time is geometric. So they ask this problem: can we quantize the Riemannian geometry? And they have done that job. On the other side, you have a string theory that comes from a quantum field theory perspective, and they also managed to quantize. In quantum field theory, you have this notion of you have, for example, in electrodynamics, you have fermions interacting through bosons. So there are this notion of a quantum of the field, like a photon, a gluon on the strong force. And a quantization of gravity in this framework is expected to have a quantum of gravity given by the graviton. And the string theory managed to get that quantization, and they have there a particle-like excitation that behaves as the expected spin to field, the graviton. But they came from a different approach. They have a field placed in a classical background space-time. And the loop quantum gravity is, is quantizing the space-time itself, the metric of space-time. So it's interesting to see the two approaches, because in quantum field theory, the framework of quantization work nicely because you have these fields fluctuating in a not dynamic and a static space-time. Usually you can work with Euclidean space or Minkowski space, or like in string you work with more general Riemannian spaces. So these two frameworks are like half a century of work. They come from this, I think they have the same origin in the 50s with some important work of Paul Dirac, which the idea was we have in nature a system where the Hamiltonian, when you act with the Hamiltonian, the wave function, you get zero. So there is no, in some system like gravity, you don't have a notion of time in principle, a priori. So the idea is if you have a Hamiltonian work on a wave function that gives zero, you should look at the inner structure of the wave function, the Hamiltonian, and find two parts that you can break apart, and then you make an equality between the two parts so that you can evolve one with respect to the other part. This system is called a Hamiltonian constraint system. and gravity is the main. Also, nonlinear, non-abelian gauge theories like QCD is a constraint system, but more simple if you think, because you can place that in space-time and have a notion of time. But for gravity, you are dealing with space-time itself, so there is no where you put the field. You need to be more self-consistent just with that object. And Dirac started that program, and in the 60s, uh, was born a model that I think has inspiration that was applied to more to condensed matter physics. It was called sigma models. The sigma model is this idea like if you have a particle and let's moving, you can study that particle move, but you then constrain the particle to move in a sphere. That give you constraint on the equations of motion of the particle. If you manipulate that constraint, you can have a notion of the particle moving on some metric given by the sphere. And then you generalize that to fields and come string theories and generalize the particle to higher dimensional objects. Instead of have a particle tracing a word line, you have a string trace a word sheet. But the dynamics is constrained then to the word sheet, so it's a constrained model. And basically, their action, their Lagrange, their model are this kind of sigma models where the field is each position, the field is mapping the word sheet to the embedded space. So this is evolving some space-time in higher dimension. And I think it's the main idea there. And the other side, a little later, is in loop quantum gravity. We have the Wheeler-DeWitt equation. It's the same idea of a constraint system, but then work only with the geometry of general relativity. And there, after you do all the procedure of quantization, the Hamiltonian quantization, uh, it's not clear the graviton notion, but you get a notion of a quantum of length, areas, volumes. You get a notion of a quantum geometry, which is very, very beautiful. And these two frameworks is self-consistent and show it's possible. But they are already old. It's like more than half a century of working. We can think of this like the past and start think how you move from that. And nowadays it's branching to different approaches in academia and even outside academia. We have these kind of computational models. Now people are talking a lot like a Wolfram model. We are doing some work on a more computational substrate to think of this Planck scale as really operate like a computational substrate and how things emerge from there. And there are another approaches like just trying to stay close to quantum field theory and work with the gravitational field in some approximation. I, I think this is one general overview of the main approaches.
But if we take a step back, sort of, and think about the significance of this entire process and approach, what, according to you, is the theoretical importance for understanding space-time at such small scales?
space-time at small scale for computational approaches.
Yes, for computational approaches.
Computational. Yeah, so we can build on these results, like in loop quantum gravity. You got a notion of discretization of at a Planck scale. The idea is you triangulate space-time, which has a well-known method to. They have a very good method to do this. You triangulate, then you assign values to edges and vertices of this network based on the gauge group of the theory, which can be the Lorentz group or some Euclidean group SO4, or even you can work with small subgroups like SU2. Like in quantum mechanics and theory of angular momentum theory, you basically using this Lie algebra of SU2. You can apply that to space-time. Uh, and then you run the quantization procedure, and you got that in each edge, in each vertex, you can have only quanta of length or of the volume associated with the vertex on the network. So that gives you for one, at least one computational way to work with this system, which is similar to what people are doing for decades in gauge theory. Like the many of the properties of the standard models come from computational approach. The computation, we say that QCG is very successful, and that you can compute from first principle the mass of the hadrons. But it's not like you really start with the continuous theory, the Lagrangian, do the quantization, and find my diagrams and compute everything. I think the true computation is the Lattice Gauge computation. Is a whole community that is gathering results for the mass, for other properties of gluons, for confinement. We can talk later about the problem even in quantum field theory. But most of the computation there is done on lattices. You discretize we start in Minkowski space with a quantum field theory of the standard model, the chromodynamics, and you do a rotation to Euclidean space. So it's a four-dimensional cubic lattice, four-dimensional Euclidean space, and then you discretize in a cubic lattice, the space-time there. And you can show that you maintain gauge symmetry in each vertex locally in each vertex of the network. And you can take the limit of the length going to zero to recover the full symmetry in all the space. But you can work with a finite cube, four-dimensional, with the gauge, with the field of the strong force getting values only on the edges and the connections. And you run like Monte Carlo simulation to get compute correlation functions and observables. So now with the development of, in particular in loop quantum gravity, we can do the same with the gravitational field. You have one way to discretize the metric and to assign values to edges and vertices, and depending on your computational power, the resolution that you can go, but you can compute observables, quantum gravity observer there. And of course, if you have this discrete system with this microscope theory, you can apply another well-established framework to analyze the large scale behavior, emergent behavior, which is statistical mechanics and thermodynamics. So it's interesting that you can do the computational models. I mentioned very fast in the beginning the Wolfram model where you have like these hypergraphs. It's all the same idea. The Lattice Gauge Theory is a cubic lattice. You have values in the lattice, but you can generalize this to more general graph with different kinds of connections. And in looping quantum gravity, you have triangulations. It's basically if you think in 4 dimensions, and you you want to stay close of lattice gauge theory, you could just use the 4 dimensional A4 lattice, which is built out of the four simplex. So it's just a triangulation of that space. But of course, that is the gravitational field. So they are dynamic. So you have different lengths and different. The four simplex can take any deformation. But yeah, what I'm saying is we now know how to deal with these different discrete models, lattice, graphs, hypergraphs, triangulations. Here we are working with something between that's not don't have like periodicity, but it has longer range order, which is a periodic order. Quasicrystal is another way you can discretize this space. And all the time you have a notion of a network with vertex connections and values that you can put that come from your model. I have a son come here. Uh, and you can think of this as the microscope theory at some deeper scale, like we can go to the Planck scale in the computer, say that interpret that length as Planck length, and then you can say what observer can compute on a larger scale, and then all these approaches are applying the machinery of statistical mechanics, thermodynamics. So we have do averagations and compute expected values. Not sure if I answer your question.
You did. Another thing that I wanted you to talk about is quantum information theory. How is information encoded, transmitted, and processed in quantum systems?
Quantum information.
Yes. How, like, for somebody who's got absolutely no context about how this entire process works, very beginner esque example and explanation of how quantum information works.
Okay, I can build from where I stopped now with these networks that we use to describe quantum system. So one way to encode the information there is like we study correlation between the different nodes of the network, and one important quantity is entanglement. So one thing that we know how to compute in this network is entanglement entropy, and entanglement entropy is a pure quantum uh, kind of object and property, and we are find application everywhere from quantum computing. For example, the idea is to use entanglement to encode information that you can then manipulate. This kind of, if you have this network, you can think each node is a bit, a quantum bit, and you compute the entanglement. Then you do manipulation and you observe, and in principle, people are using these techniques to do the so-called quantum computation. So a basic property we want to work in context of quantum information is the entanglement entropy. And I think all these system dimensions, from dealing with lattices, with the quasicrystal, with general graph, most of the models are based on these structures, and the information is encoded in the network itself. Now, I think the hot kind of discussion nowadays is quantum computing, where people are harnessing the entanglement to do computation, and there is belief that quantum computation will be able to do computation that no classical computer can do. And but the difference is this quantum information is much more sensitive to the environment. So there are a whole field of study of how we preserve entanglement, how we preserve these quantum properties, and there are nowadays quantum computer with a few qubits, and the idea how can we scale that, preserve the quantum information to large scale, to have meaningful computers that can do meaningful computations at this kind of quantum level. Uh, Here I have worked a little in last years. I'm kind of scattering in different approaches, like trying. Nowadays, you have to be a little multidisciplinary. All these fields are intersecting. Then I was looking at this topological quantum computing. It's another way to encode the quantum information. So usually, like I said, in the network, you are encoding locally the information. Like can be a network of electrons or photons, and you think that the photon or the electron is the qubit, and so it's very sensitive. This tiny quantum part is very sensitive to the environment, so it's very hard to, if you entangle one electron with another one, it's very hard to maintain that coherence. And so another idea less known is maybe we can encode that information on this network not locally but globally. And theoretically, we have models that predict system where you can encode the information globally or topologically. Topology refers to this idea of continuously deform something. So you can go in and go back. And if there are some obstruction, then you cannot deform that, and that is an important property of that particular system. And there is a theory that say that in 2 dimensions we can have system that can encode the information topologically. Even there are some particular particles that are like predictions, like anyons, they call anyons, and because they have a statistic that is not fermions or bosons. So they give another name, anyons. It can have any other statistic, any other fractionary spin that's not the 1/2 usual fermion spin or the integer spin for bosons. And this can happen in one in lower dimension. And there are some predictions, some materials that you could encode the quantum information that way. And more recently, in the news, we see there are two important simulations, one done by Google and the other one done by a small company called Quantinuum that is partner of Microsoft. Microsoft is the big player trying to implement this quantum computation using anyons. But now it seems they have these partners and they have a quantum computer like Google, and they managed to simulate the so-called non-abelian anyons. So it's an important indicative that it's possible, even though we didn't create them in laboratory yet. Some years ago, there was a false claim by Microsoft. With 1 or 2 years later, they said, we got, I don't know, maybe Majorana fermions signal in some experiment. But then was not the real one, and they back up. Now they are doing simulations and showing us it's possible. It would be nice if you can implement this because it gives you a more robust, harder level protection against decoherence. Like I was saying, if you have just one electron, it's very hard to protect that against the dissipation of the quantum information. But if the system is an electronic system, but the information is not encoded, the quantum information you wanna manipulate and you wanna do some implement some gates to manipulate and do some computation, and then make some measurement to get the result. The result is very hard on that level. But if, for example, Majorana fermions theoretically could arise on the edge of this two-dimensional electronic system, so all the stability of the system gives stability on the quantum information on the edge. So you don't need to worry about locally protecting the electron. It's like the information is in a quasi-particle excitation that is in another scale. And in principle, you could manipulate that information like you do with electrons. It's just a different operations you need to do. For in this topological setting, for example, anyons, the way people think you could implement a gate, for example, would be just moving one anion around the other. So if you have this edge state, you should have some way to move the state around. So because of the global encode of the information in this topological system, it matters how you move them in the two-dimensional space. They call that the braids. How you braid one around the other is important. And then in the end, because they are quasi-particle excitation, you can bring them together, and they can annihilate in a precise way that you can recover the information of how the quantum information was manipulated in the between with the braid kind of gates. So this is another interesting subject, this quantum informations research, like quantum computing, and now it's growing attention on the topological quantum computing. But even just a quantum computing, the things is going fast and is scaling. I was in contact with another people which is doing uh, forgot the name now, but there are different approaches to how you can scale just a quantum computing. The error correction codes are getting more and more robust.
What do you think are the most foreseeable breakthroughs in the quantum domain?
Become like I was saying, I think this topological quantum computing is something hot that we are in the edge to have something big here. Now there are new companies that is buying the idea and doing simulations. And I can defend my side with the work on quasicrystals. I think quasicrystals is just a brand new concept. Like was discovered in 82, and before people was thinking that was not possible. There is a theorem in crystallography that says it's impossible to have a diffraction pattern. You see like five-fold symmetry in diffraction pattern of some atomic material. Is the theorem says it must be a crystal, two-fold, three-fold, four-fold kind of symmetry, six-fold, not five. But then in 82 was discovered before mathematically was well established the possibility. Even Penrose work on this. So one of the main quasicrystals known mathematically is the Penrose tiling, a two-dimensional way to tile the plane with two different tiles. It has longer range order, but not periodic. And then it was a boom on research on the 80s and 90s. But they didn't break through to applications. We don't know much about applications. And even the main people work on that change field, like Kitaev, work on quasicrystal, then start work on topological quantum computing. Steinhardt was more working cosmology, other things. Even people work on the mathematics, start to work on other things. Anyway, what's not that? People papers around over the years, but I think it was not so huge when it was coming from the 89th because people did much more complicated. People didn't find application, immediate application. But now I think is a reborn. There is a new wave coming. I was looking Google Scholar and there are hundreds of papers just now this year. uh, and people start to think applications, in particular in the quantum information side. There are models on spintronics and photonics using quasicrystals. And a nice development, I think it was mainly for some MIT group. There are, for example, it's a good example, they are manipulating two-dimensional graphene material. And depend on the angle that you mix different layers of you put different layers of graphene by different angles, and you have an emergence of a new kind of structure that can be more exotic or can be crystalline, but also can be quasi-crystalline. They call Moire quasicrystal. It's a kind of pattern that arises, you know, when you shift the layers to a particular angles, then you can put a magnetic field and manipulate these excitations. This, I think, is some breakthrough coming in that direction. That one of the application could be on this topological quantum computing. I have done some work where we show that you can recover the anionic formalism on the quasicrystal. Basically, if you would be able to grow and inflate, grow and shrink a quasicrystal, it's complicated. But if you could control that at the quantum level of the quantum material, that is equivalent to, it gives a Hilbert space that is equivalent to the Hilbert space that arises when you study anionic system. And I think there's a lot of potential there, but that is more kind of maybe speculation from my part. But there is some concrete results, like I mentioned, the more result of graphenes on the MIT groups and many other groups with important results on spin system and photonics. Uh, there are different kind of quasicrystal being produced now. So this, I think, is interesting. But the the big breakthrough we are expecting is a large scale quantum computer. And you have China, you have Google, you have Microsoft, IBM. So it's coming. And we have now this artificial intelligence system. So a lot of breakthrough will happen in that sector. And when you merge, like when you have a large scale quantum computer and put a larger language model on top of that, we can imagine big things coming. We didn't talk much about AI, but I'm very excited about the development on AI system. A lot of breakthrough will be possible now. Uh, we can, we can say that the language of nature is a kind of mathematics.
Hmm. Hmm.
Don't know if you agree. Uh, and you have all these languages. Like I speak mainly Portuguese, and I have a. It's very hard for me the other languages, but now I can talk with these systems and discuss old Chinese text that they can translate easily. And so it's a breakthrough on the communications that can help people to start think differently. And mathematics is very hard for many people. For a lot of people have difficulty with mathematics. So usually you think that they would not contribute to discover the code of reality to the deep underlying discussion. But now or soon, everyone will be possible to come with something, some new creation, some new discovery on fundamental physics. Because you have a translator, you can have your AI assistant. You talk in English, and it gives you the mathematics and explain everything. Uh, so we will have much more people think about the current problems. So I think we will have much more solution in every field of research. Anyone can be a researcher soon. Uh,
I'd like for you to go a little deep into this particular matter. In the day and age of artificial intelligence and such technologies, how can an aspiring researcher utilize these technologies to their advantage to become better at what they do? That is research and development.
Yeah, very good question. Yeah. Nowadays is already very useful for studying because the system already know a lot about uh, the more like things that have more data, things that we know better have more data available. People talk more about. There are more courses in some established disciplines. So to study the established disciplines is good. Uh, it can guide you in solve some problem, even if it cannot do perfectly. It helps give insight how you solve a specific problem, and then you go back and forth. And they are getting very good on coding. And nowadays, if you want to do a research on condensed matter, quantum gravity, quantum field theory, just in this short talk, we talk about a lot of computational frameworks possible, like Lattice Gauge Theory. Uh, Looped quantum gravity has this spin-1 models with all the computations doing in the computer. Uh, the computation string theory, all the new, more recent models. So all these require coding, which takes a lot of time. If you go code in Python, C, C++, it's a lot of time, and you can save now a lot of time if you can specify very precisely your problem. Then you can go back and forth with some learn some large language model. It helps that to get concrete computations. So it helps learning. It helps with the coding, computation. First, you ask about someone that is coming now and aspiring, so it's learning. So the learning process is very good. You can put a PDF in this model of a paper and get a first insight. Then you can go faster because one important thing is the for research is the bibliographic review. You don't wanna reinvent the wheel. You wanna know exactly where your field is, what's the open problems, what the current proposals, and then how you can contribute. So all this learning can be much faster now. So sometimes you take a year to cover a specific field. Now you can do in 1 month, maybe. So the learning, the coding, then you understand the problem, where you are, the next step, and you come to one idea, one model, you can make a specific computation. Usually, you would take a lot of time to implement that computation. Now, if you can translate that to computational problem that can be solved with some Monte Carlo method, some numerical method, then you can have the AI system coding for you. And you have a different ones coding, and you compare, test, and you can even use it for learning coding if you want to do yourself the coding part. They are very good with teaching coding already. They are very good. Let's see. To get new ideas yet, I didn't find yet. Like you need to give a good input to get a good output currently, but it's already very useful. And if you have more resource, what I'm trying to get, we here we would like to have a specialized model, develop ourselves the model. For example, Quasicrystal. Uh, there is not much. It's not solved. For example, if you wanna compute a Schrodinger equation in three-dimensional system with a aperiodic potential, it's very complicated. If it's a periodic potential, there is a whole theory, the block theorem, that is a main thing on that condensed matter physics, solid state physics. And people know how to compute, extract information of periodic system. But for a periodic system, we can compute only one dimension, maybe two dimensions. So I would love to have a model that we can train in every quasi-crystal paper from the 80s, 90s, and the more recent. And you can discuss in details the problem and do computations. So I think you can apply this to your field or any field. If you have resource, you could have a specialized AI assistant in your particular field that understand your problems, the techniques. I think things will go much faster now.
It's been a very in-depth conversation with you here. At the very end, I would like for I would like to ask for your advice for aspiring physicists or those who are curious about these topics. What is your advice to them?
So the advice for who is interested in these fields, the one advice you said, I mean,
Any advice for people or for aspiring physicists and for in general people who are interested in these topics and this domain.
okay, people interested in these topics and people that wanna do research in these areas. Yeah, we just talk about the AI system. I think it's important now to everyone coming now is a new area, is a new era, is a new time. Don't be fooled by the pessimists that are worrying about the AI. It's coming. Everything is changing, and we wanna work together with these AI systems. Uh, we wanna improve them and work together. So this is important now. So you can use that to learn faster. And also, I think we should be open-minded and stay tuned to different people are touching same problem from different perspective, and sometimes they use different mathematical language. So for who is coming now, maybe it's possible to get familiar with different kind of jargon, different ways to deal with the same problems. Like from you can get some background information, quantum information theory, quantum field theory, basic quantum mechanics, uh, the geometry tools like for gravity side. So not be afraid to explore the different possibilities. For who is coming now, it's not important this competition. If you look the past, they are competing to say, I have a better theory, I have that. For us, it doesn't matter. We want to use the better thing for each one to understand better things. And who I think it's important also to my personal view is the technique it's in itself is doesn't mean much thing. You can build anything that you invent a new thing, a new technology, and you can build anything with that. And it's just that is so we need to pay attention to the broader context. Uh, I think it's important for anyone to have their mission, like their what are your mission, what mission, what your purpose, why are you doing this, why you doing this computation, why you study this mathematical framework. It cannot be just a job, a money, because the world is going very fast, and I think we should be worrying about helping humanity going forward. And this is a good place, like fundamental science, understand mathematics, physics, and communicate that, chemistry, all these coding things. Because there's a thing not much in the past that try to disassociate the technique from other humanity things. So it's time to bring all together. Science, mathematics is humanity, is part of humanity. We are creating things uh, that come from our desires, our purpose. And on the technical part, I used to give a particular hint that comes from my study of different fields. To work in different things, usually you are searching for particular things that is general that you can use in different places. When you talk about quantum gravity, I was thinking good technically talk about the Lie algebra, Lie groups, and their root systems. But I think it would be too much techno. But we talk about the unification and all these different approach. One thing I'm finding is appearing everywhere from gauge theories, from condensed matter physics, quantum information, is this basic math of Lie algebras, Lie groups, and their associated lattices, quasi-lattices. So if you are going to a theoretical kind of research, I recommend to understand deeply that stuff. And then from there you can go from to different field applications. Yeah, who is coming from the quantum graph perspective, we will say that SU2 is one of these little Lie algebras and Lie groups. It's kind of building block of reality. There you have real numbers, complex numbers, quaternions. So it's a little engine that works in many different fields. Even now for these neural network models, the way that it's computing, we are dealing with this basic math. So it's a good start point for theoretical physics. Talking more from my specific thing.
That
Yeah,
was wonderful, Dr. Marcelo Amaral. It was a lovely conversation and just as relevant in terms of the current standings of the quantum domain and the future of its advancements. Thank you very much. Thank you so much.
thank you.